So how does one of these tests actually work? And the system that I handed out to you is a system that would be used for urine. Blood is a little bit more complicated. And here, there are a whole series of very, very interesting cultural issues that come up. When we take blood, we have a particular device, we stick it in a vein, the blood gushes out, you've seen this, it's called a vacutainer, it's fine, but it has sharps, it's expensive. But in practice, about all you're going to be able to get in blood is one finger prick. So all the analyses that you do have to be done with one finger prick. And basically, people don't like giving urine samples. They certainly don't like giving feces samples. In dry climates, you can't get saliva. But almost every culture will let you take a finger prick. But a finger prick is not very much blood. So the devices that we're working on are devices in which you take a drop of blood on the finger, no preparation. Look at these little things that you have. Imagine taking the drop of blood and putting it down on one side of the piece of paper, and then on the other side of the piece of paper, a series of colors appear. And those are the diagnosis. They provide the diagnosis. That's the idea, and that works. It's terrific. And these colors here are simply colors that give a sense for the range of colors, and it's a technical issue that's not important. But there is another important issue, and that is that I say it gives, diagnosis, but who's going to do the diagnosis? Because we've agreed that those of you who are doing this experiment actually don't have any medical training. And if you go to a developing world country, the money is in short supply, the technology is in short supply, but the shortest supply is doctors. And you just can't take someone who's trained doctor and send them out into the bush, 4 days of travel over rutted roads to go see a village of 200 people. It's not a workable thing. So the vision that is emerging in people who pay attention to this area is that the healthcare worker of this world is going to be an 18-year-old who has a backpack full of these devices that you have got and an AK-47, because an AK-47 is really very useful in making your way through some parts of the world in which these systems are most useful. But this crucial thing that he's going to have as a healthcare tool, his one sophisticated piece of equipment, is this. And it's a very interesting statistic now that these things are selling right at the moment something like 40 million a month in India. There are 1 billion people worldwide who have access to broadband portable stuff, and everybody in the world in a couple of years is going to have a cell phone, everybody. So the notion is that what one will do is to turn over this little paper chip. There'll be a series of colors, and this teenage kid will take his camera and he'll take a picture of the colors, and that picture will go back to some central laboratory somewhere where it will be analyzed either by a computer or maybe by a real doctor. Now we've done this, and this slide sort of illustrates the notion that one dip the device in the sample, you get the colors, you take a picture of it, and then you ship it to a computer. And we've done it in the laboratory, it works fine. We can ship signals from room to room. It's a long way from shipping from southern Namibia to northern Namibia, but it'll work, I think, perfectly adequately. But there is a really interesting problem there, which is that the cell phone systems are really bad in many of these countries. So how do you deal with shipping information that's pictures where colors are important over very, very bad telephone systems? Fortunately, that problem has been solved before, and it's been solved basically on Mars. And the problem there is that the bandwidth, that is the reliability of the signal coming back from Mars, is very poor. It's a long way away, there's not much power. How does one make that work? And I won't spend my time or yours, since it's not my expertise, talking about it, but the guys who send back signals from Mars know a lot about how to get a lot of very high fidelity information across a very narrow bandwidth channel. That is a very bad telephone system. So in a sense, I regard this as a solved but not engineered problem. Now, let me give you one bit of high technology. I think it's always good to mix the practical stuff with high technology. And this is another one of these chips, the same size. And each colored dye goes in a little channel, and if you look carefully, you notice something that might be interesting, which is these flowing, wicking fluids seem to cross one another. And you say, you know, I don't know how you make two liquid streams cross. And of course they don't. What happens is that one goes under the other or goes over the other. But then that raises another question, which is how, with a simple piece of paper that's just doing nothing more than wicking, do you get things to go over and under one another? How does that work? And there's a very, very neat technology that has been developed, we've developed, to work on this problem. These pieces are the paper, and the areas that are gray are made impermeable to water. And then these pieces are literally double-sided carpet tape. We need things that's cheap, so it's plastic tape, water doesn't go through it, and it's sticky on both sides. It's what you use to stick your carpets on the floor. Very inexpensive. And the black holes are holes in the carpet tape. So that what I'm doing here is simply stacking multiple layers of tape and paper. Let's follow a drop here. This drop of blue ink goes in there. It goes through that hole. It goes down in that spot. It then wicks its way on that channel down through that hole into this, distributes itself by wicking into these four places, goes through those four holes, and then ends up in those four spots. What this enables you to do is to take the single drop of blood and then run it into one of these systems that has many test zones so that you get many answers. Because the characteristic of this kind of medicine is that you get one shot at the patient, basically just one shot. So you get one drop of blood, you need to make, we don't actually know, but 16 or 60 or 500 different assays on the one patient at one time. And this very simple technology enables you to do that. And this is the way that the basic test will work. You take a drop of liquid here, it wicks its way, in this case, into the center of the chip, and a series of colors then appear on both sides, and these colors give you indications of what the disease might be that the patient has. Now, let me finish with another example of technology. It's a little bit different, but it's relevant to this and actually important for the development of this area. There are circumstances, for example, assaying malaria, in which what you have to look at is cells. You basically separate the patient's cells and count the number that have the malaria parasite in it. I mean, it's an important part of staging malaria. And to do that, you have to be able to separate cells or isolate serum and cells or do something of that sort. And the way we do this here is to take the sample of blood, put it in a centrifuge, which is a metal wheel that spins around, driven by a motor, and the G-forces, the high force of apparent gravity, squeezes the cells to the bottom. Works fine. It doesn't work nearly as well if you don't have a centrifuge and you don't have any electricity. So now the question is, if you were there, what would you use as a centrifuge? We thought about this and we said it has to go round, and it has to have another important characteristic. That is, if it gets lost, we have to be able to replace it. And it has to have another characteristic, which is it has to have no value so nobody will steal it. Those are all important. And we had the idea of an egg beater. They're everywhere, they're cheap. And by the way, after you sawed off one blade of the egg beater, it is completely useless for anything as far as I can tell, so nobody's going to steal it. And so what we did was simply to work out a procedure in which we take this single drop of blood, we suck it up into a piece of polyethylene tubing here, we seal off the ends of the polyethylene tubing with a Bic lighter or a hot coal or whatever happens to be there, tape it to the egg beater, and then someone with a strong arm sits there and spins it. It turns out to be roughly the same G-forces that you get out of a $5,000 benchtop centrifuge. So it really works quite well. We were very proud of ourselves about this piece of technology, and we made it look like real science. We did differential equations, we did the physics of egg beaters, we wrote equations. I mean, it was really, really very apparently impressive stuff. And we sent it off to a journal, and it came back rejected by overnight mail, just instantly. And I knew the editor, and I called him up and I said, I don't fully understand this. I mean, it seemed to us like really neat stuff. How come it's rejected? And his answer was, yes, I looked at it. I determined that it was clearly socially useful and clearly valuable in the medical system, and hence inappropriate for publication. And you sort of go, huh? I mean, what am I missing here? And I think his point was that if it's simple and useful, it's not science of the sort that scientists like to see. And I think there's a little bit of an issue here of our society getting priorities straight. I'm all for doing fundamental science, but I have to say I also think it's very important to fix problems. If we can find ways of making healthcare so simple, so robust, so cheap, that it can be done in Harare, which is the great slum outside of Nairobi, or the Mumbai slum, or the favela outside Rio, then we should be able to bring that technology back into the United States, fully developed, and find a way of reducing the healthcare costs in our system. And I think everyone will benefit. Thank you very much.